Let's get started. We're recording. So on Monday we started the discussion on CNNs, right? And I gave you all the intuition and kind of the theory of the differences between just a regular neural network and then something like CNNs. Okay. So today we started the code on Monday, and today we're just gonna continue with that. Um, and work on the script. So I don't think that's going to take the whole class period. So then once we're done with that, I want us to go back to like Colab or Kaggle. So we're still having problems with Scholar. I don't know what the issue is, but they haven't figured it out in West Lafayette. So you guys still can't log in via the gateway to run Jupyter notebooks. They gave me a workaround where you can SSH and you'd have to run the job without the Jupyter. Do you see what I'm saying? So you'd have to make your Jupyter into just a regular Python and run it that way. So I'm working on that. If I can figure out by next week, I'll provide that option. But otherwise, I do recommend that you start playing with Colab. You should be able to do this with Colab or Kaggle, right? How many of you have started playing? I know I did a demo of Colab, right? So how many of you have tried it? I just want to see how it's going. If, hmm?
I think I'll see.
Yeah, if you have your own GPU, that's great. I mean, I have my own GPU, so this is why I'm actually I never use Colab, but you go ahead. You have your own GPU?
Yeah, I was gonna upload because I was trying to do first read from my local, but if I don't want to read from like the drive, then it's gonna take really long. That type of distance. And then it's trying to
Yeah, no, I agree with you. It's
it's a
using,
really big data.
you have to load the data set close to the where the computing is. Good with this. I agree with you. So with Scholar, you have a 1 terabyte of scratch space. So you can just upload it there and then it's going to read from the local machine on the web. So yeah, we have to solve this. This is new for me this semester because we've always had Scholar. But I want to see, I just want to know your experience with Colab, how that's going. How many of you have tried it? How many of you have loaded the data? So you've done it?
Yeah.
Cypher 10?
Yeah.
Did you load all 60,000 images?
I get
MNIST.
Yeah.
Okay, so you guys, okay, MNIST is
So
still 60,000. Where do you load it? How do you load? Oh, okay. So you're just using the library and downloading it. Okay. Yeah. So the challenge, actually, I think it's like what he was saying, is going to be that with Sci-Fi, you have a folder of images and you're going to have to take all those images and load them somewhere,
it
right?
looks like it does give you enough to upload,
Yeah.
but you have to be can't do it.
Yeah. Okay. Yeah. So this is one of the things that I was saying. So I've actually never done that with Colab. And one time I played with this and I didn't think it was that easy to load files on it. So it's something that if we have time today, maybe we can all just like kind of try because that's one of the best options we have currently is Colab. The other one is Kaggle, unless we figure out I'm starting to just give up on that Jupyter that gateway option with Scholar, and instead we're going to have to use only the SSH option because they haven't fixed it yet. So, but we should be able to do everything in Scholar or Kaggle, I assume. So, yeah, keep me posted if any of you are able to load the entire Cypher 10 into Colab and start training, and just let me know how long it's taking, all those things. I'd appreciate that information. But I'll be working on that too. All right, so yeah, so today we're gonna continue with MNIST and we're gonna try to, just play with that, finish a full CNN from beginning to end, and then maybe hop on this Colab thing and just see if we can run it from there. Yeah. and do some comparisons in speed. Sorry, yeah, go ahead.
Yesterday, I emailed you regarding a due date for the cipher.
Oh, that's right. I think I replied.
Yeah,
Yeah. So Cypher 10, I was thinking in 2 weeks, stage one, and then stage two in 3, 4 weeks. So it's kind of like I will give you guys like, some of you can start presenting this week, and then the rest of you can present the following week. So I'm gonna do it and then we're gonna name the winner at the end of that. Does that make sense? So that way, some of you are faster, some of you are slower. I want to give you enough time. Everyone needs to present this. Okay.
So first part, 2 weeks.
Yeah, the first part, stage one, would be in about 2 weeks from today. So if you think about it, today is Wednesday. Next week is the exam, right? The following week, we do stage one. Okay. Which is essentially just repeating what I'm doing today, but with sidebar. You have to use a CNN, multi-layer perceptron, DLNet, and just get the best performance possible. And then after that, I have to give you some background on ResNets and transfer learning. We started covering that on Monday, right? And so that would be stage two, and that could be either 3 weeks from today or 4 weeks. And after that, the only thing that might be left is a small term project where I want you to do a PyTorch model and just use Onyx. That's it. Got it?
You think the project would be more like a flat, or you think it's gonna be like?
It's a project that you can
Okay.
do in groups of three, so that's the advantage. So
Oh.
you can work with teammates, but what I want to show you is that you can train something in Torch and deploy it on the web, on GitHub. That's really nice because, one thing is to do something and you do it on your computer. Another one is to send a link to your friends and say, hey, use my AI model on the web. Right? So you can totally load it on GitHub, and it's exactly how we did the Perceptron, except we're not using PyScript, but instead we use the Onyx framework. So that should be an easy project. But yeah, that's it. Yeah, go ahead.
The project, like when we announced it.
Well, it can be anything. So, oh yeah, officially. Well, that's the project. So the project, I just haven't covered the topic of Onyx.
Oh, so like, would it be like, we
The project
Yeah,
is
like,
due
when
the week before finals.
And-
You can start it now if you want. I just haven't covered Onyx is unfortunately the problem. Yeah, but it would be, imagine the wine quality that we did in PyTorch, right? Remember that data set? So we did wine quality. You give it 11 features and it would predict a class or a rating. So you do that model. You could actually, that could be your project. You just do that model. But now what I'm going to show you is that you can export the model into a file called Onyx. And then you can load that file on a website. And then with a little bit of JavaScript, you access that Onyx file so that you can now run it in the web. That's essentially the project. So you already know how to do the machine learning part. You just don't know how to export the model and then how to load that model into GitHub. Got it? Yeah. So I'll try to do that as soon as I can. Maybe next week I'll try to squeeze it. But yeah, those are the things that are left. And like I said, if Scholar was working, this would have gone more smoothly. All right. Anyway, so we are recording. Let's try to finish up our script of MNIST, CNNs. I've given you the theory, the intuition. So today is really just about finishing up that script and getting it to work. All right. And then we'll try Colab and repeat the exercise. All right. Let's go to all. Okay, so I'm just looking for the file. So it should be in CNNs. All right, in class MNIST, so that's what we were working on. We're just going to finish that up. Right, I'm going to need my code. All right, so we are here in CNNs, and we are basically playing this version. All right. So we had covered all these, I believe. Let's the prompt. Let's activate the environment. That. And it should be 937. 25. Yes. 365. All right, so let's click on this. Right, and I believe we have done everything. We had loaded the data, and we were just getting ready to start creating the architecture. Okay. So I'm going to just rerun all of this, restart and clear the kernel. All right, so we are ready to go. So this is my code. We basically stop here. So just before CNN architectures. So let's go ahead and run this. Okay. So I'm not going to repeat all this. We talked about it in the previous discussion. All right, but the data is ready, right? The train and test it. So just take a look at that video if you don't remember, and you can see what those things are about. But our data is ready, pretty much the same format. So now what we are going to do is create the architecture. So I'm going to, and notice this is just a CNN architecture, but we can try other things. So I'll need to explain. This is really where the one thing that's new this time around. Everything else should be pretty familiar. All right, so let's take a look here. So essentially, we just like before, where we created a class for MLP, one for DLNet. Now we create a CNN. I've explained to you that this is a convolution instead of just a simple matrix multiplication, but and I showed you kind of the algorithm, right? You've seen it even in 2 for loops. I gave that discussion on Monday. That algorithm, though, is still implemented by matrix multiplications. That's the trick that you have to understand. Like the thing that might confuse you sometimes, that you see these algorithms and they're no longer just a matrix multiplication, but just think like somebody very smart looks at the algorithm and then they break it down into the operations and then they just implement those as matrix multiplications. All right. And so that's why we can still use the GPU for this, right? And efficiently. CNNs are very good for GPUs, or GPUs are very good for CNNs. So we create the class. Just like before, we inherit the NN module, which gives us a lot of the constructs. We have two functions, just like before, init, and then we have the forward function. But now we're going to have a few things that are different. So now we are going to use this construct here, NN sequential, if you see that. We haven't used this before. In the past, we would just create something, X, it would go into linear 1 to produce H1, then that H1 would go into linear 2 to produce H2 and so on, right? So that's how the data would flow through the neural network. This one is different. And you can use this for your previous machine learning models that you've written before. So there's two approaches, right? The sequential approach, this one, or the previous approach. I like to use this sequential approach with CNNs because CNNs have a lot of code. There's a lot of lines per layer. You know, before we used to just have like 1 or 2 lines per layer, but with CNNs we have more lines. And so sequential just becomes easier. All right, so what you do is, if you notice, you know, X is not going in here and then coming out here and then the output of that going into the next one. So what I mean is we don't have this anymore. We don't, if you notice, we don't have like an X equal linear X, right? So that's not happening. And then that X would become the input to the next one. So like another X, and now linear 2, right? X. We don't have that anymore. So this is just another way of writing things without that thing, an argument going into a function and then the function returning a value that goes into a variable. Instead, we just define the layers essentially like this. So we just say, you know, a layer from 1 to 6. Okay, hold on a minute. Yeah. All right. So what I was saying is there is no X that goes into this and then the output goes into the next one. Instead, you just write the layers. So you say that the first layer is a convolutional layer from 1 to 16. And then down here, if you notice, now the next convolutional layer, it goes from 16 to 32. And then you do this flatten operation, and that makes it into 800, which goes into 512. Do you see that? That's kind of the connections just like before, but this is a little bit different because it's got more things going on. Okay? Now I'll show you, we'll play with this just so that we can figure out how to calculate values like this. So that's after this. But essentially, I want to show you the overall structure, right? How the neurons are connected, essentially. So one way of doing this is you create this variable self.model. That's going to be your CNN, okay? And then using NN sequential, you define the whole architecture of this network, okay? Then down here in the forward section, notice we give it inputs, right? These would be the X's. That's just a different name here. Inputs go into the model, and the result of it is returned, right? That's essentially the logic. So then, but notice here, nowhere do we specify that inputs are coming in. You see that? The variable inputs does not need to be defined. But this structure assumes obviously that there's an input. You don't have to include it. All right, so now let's think of the structure of how this works. So for a convolutional neural network, you can have as many convolutional layers as you want, right? So you want to add 8 convolutional layers? Go ahead, right? If you have a GPU with enough power, it'll probably work, right? ResNet will be pretty big. So you have here then the convolutions. You can see I find one convolution, which is this whole block. Then the second convolution, that whole block. And then after that just comes the feed forward layer, which if you remember is where you don't do the convolutions anymore. It's just going to be a regular feed forward layer, right? But the thing that has to happen is before you go into the normal feed forward layer, you have to flat the output because the output of convolutions, remember, is kind of a cube. We talked about this uh, on Monday. So if you read the notes, right, I'm kind of using this architecture, right? So I have one convolution and another convolution, and then whatever cube comes out of these convolutions, you just flatten it. And this dimension is different. Um, this dimension actually you have to figure out. This number, you have to know what it is, but I'll show you guys how you can do that easily. Okay. And then once you have that notice, you just connect it to your normal classifier. So if we look over here in the code, if we work our way back, this is pretty important here. This is exactly what you learned previously. Nothing has changed there. So if I can use the markers. There. All right. Okay. All right. So again, I'm trying to focus just on this area. And just before just before we have the flatten, which is basically what comes out of the solution should be a cube. All right. This gets flattened into a vector that, according to this, is going to be of size 800. And then all of these layers should be exactly like the layers that we did for Iris and the layers that we did for the wall quality data set. So I'm going to try my board here, my whiteboard, see if it works. Classic. Okay. So that one, if I remember correctly, is so you have MNIST images, right? Which could be 784 or they could be just 28 by 28, right? So they go in like this actually, not like. And so images go into the network. You have your first convolution. On one, right? That has 16 filters, I believe. Then you have another convolution. Two, and that produces something that is, imagine it's hypercube of some type, especially if it's color images like that. You see that? And so now we flatten this, right? And according to the example, by flattening, we get a vector of size 800. Do you see that? And then after that, I believe the next layer was 512, right? So that would just be exactly like how we were doing things. We just add a layer 512 to give it a little bit more room. And then I believe after that, we had the classes, which are 10. So as you guys know, to create layers like this, feed-forward layers, normal layers, you just use nn dot linear, right? You guys know that. So we're using nn dot linear. And we've already defined many times that nn dot linear is nothing more than w times x plus p, right? The previous layer and it's the next layer. So you can add as many of these as you want. And what's new really is this evolution, and then we need to flatten. Okay. So now let's go back to the Jupyter notebook. So I think I need to stop sharing here. Share here. So we should be sharing. So that's what I was saying. So notice it's just an n, and after the flatten, you have a normal n linear from 800 to 512. You want to add some activation like rel. Then you have another n in linear from 512 to 10, and then log softmax. If you remember, those probabilities are made to add up to 1. Does that make sense, guys? Read through the notes, please. If I have examples, additional examples there about softmax, etc. Okay, so then that's pretty easy. Then I would say, from here to here. So then here's where you put your convolution layers. And notice that for this, we're going to use a new construct called con2d, so nn con2d. And it takes 4 parameters. So we have to think about how we're going to do this. So we do the convolution followed by a ReLU activation followed by a max pool function. So this is one way of doing it. Or you can do it without max pooling, but then you have to change the stride. So that's the trick. So the stride, if you have stride of 1, then the image is left as is, essentially. You see that? So, and it doesn't make it smaller. So then you have to max pool it to make it smaller. But if you have stride of 2, then it's going to reduce the image, right? And so you don't need the max pooling. So you just have to use one or the other, and be careful that you don't use max pool and that you set the stride to 2, for instance, because then you would be like duplicating the shrinking of the image. Do you guys see that? So that, or the reshaping of the image. So that's it. So we just have to understand. So essentially, if you have black and white images, then you have 1 channel. So this is 1. If you have color images, you have RGB. So you have 3 channels. So this should be 3. Got it? That's it. Then after that, you have the kernel 16. So these are the filters that you're going to apply. Essentially, think of it as 16 versions of the image come out. And this number usually needs to be the same as this number. Okay? So it's similar to how we do the neural networks where we have, 4 to 5 and then 5 to 7 or whatever it is. So it's a similar idea. But just think of it as these are filters. So 16 is a good number to 16. The kernel size is literally what we talked about on Monday, is just a little grid that you're going to apply. So you're going to have 16 filters that are 5 by 5. Remember, the values there are going to be just random data, and during training, those are the weights that are learned, okay? So that you know how to process your images and transform them. Then you have the stride, which I already talked about. It's essentially, if you set this to 1, then you have to have a max pooling option. And then padding, you can set it to true, essentially. So you have padding on your images. And this just has something to do with how it applies the filter at the edges of the image. Okay, then you have ReLU, as I said, the activation, and then just set max pooling. You can just cut it, use this default value 2, 2. So that's it. So you do the first convolutional layer, and then the output of this, notice, so think of it as the X data, it's going to go through this. Okay, so it just goes through these 3 lines. And then when it comes out here, it goes to the next 3 lines. So in the next 3 lines, we repeat the process again. So we have another convolutional layer, the 16 from here. Output becomes the input here. And now you say that you want to apply 32 filters to this one. So even more. Kernel size is still 5. This value could be like 3, for instance, also. But 5 is, a good one for this data set. Stride is 1. Again, padding is 1. ReLU, and then you do the max pool 2, 2. So it makes the image from, 28 by 28 to 14 by 14. And all of that is discussed here in detail. All right. So once we do that, you have, as I said, when it, like right here somewhere here, you have a hypercube, and that hypercube you're just going to flatten, right? And you have to figure out what that dimension is. So in this case, I figured it was 800. And then from there, as I said, you add another layer. So from 800 to 512. And then from 512 to 10, which is the 10 classes for MNIST. And that's it. Any questions on the architecture? And, obviously, what if you wanted to add another layer? Then you can just do something like this. That's the point of this. But make sure, so this would be convolutional layer 3, and then this would be 32 here. Just like that. That's it. You can add as many as you want, and maybe that would give you an advantage. You can certainly try that for the competition. Obviously, that's more weights that have to be learned. It's going to require more memory, slow down, train. But that's kind of the point. Any questions? Yeah, that's it. That's essentially it. And this is your first of the advanced algorithms in deep learning. So there's the normal deep learning structure, basically, and then you have these algorithms. And CNNs is one of the powerful ones. So there's really just like the 2 very powerful algorithms are CNNs and transformers. Transformers are what allows us to have something like ChatGPT. And then CNNs are what allows us to have those really great images from DALL-E. And so those are even more advanced algorithms, but they still use anything with images is very likely to use CNNs somewhere in there. Okay. All right. So I'm going to remove this layer because it really slowed down my computer. So I'm just going to keep it at the 2 that I had. All right. So now this architecture should be created. All right. So now one thing that's the next problem that you're going to encounter with this is we'll have to do essentially with like the shape of the tensor, right? So you're getting an image. PyTorch has a very specific format for images. It wants images to be in a specific order. It wants the channel to be in a specific place. So that's one of the things we have to do is just make sure that our data is in the right format. So that's the next step. I'm going to go back to the code here. All right, so we have now the train loop. And there's just like one or two little things. All right, so this is the train loop. Just like before, it takes the number of epochs, which you know what it is, the model, the loss function. This is a classification problem, so it's likely going to be cross entropy, which we've discussed already. We're going to use an optimizer, the atom optimizer, which is the process that does that whole gradient descent thing, the calculus, right? Calculates the gradients, calculates the update to the weights, and then it makes the update. All right, so here we have the basic idea. We have the two for loops. We have the number of epochs, and then from train DL, we grab XB and YB, which is basically a batch of images with the corresponding labels. Now, the labels are going to be very likely in just like a 3, a 7, but as you know, the output of the model is a vector of 10, right? So it'll compare integers to vectors of 10 for the classes, but that actually is not a problem. PyTorch will handle that for you. So here we have, I was playing with reshaping things, but essentially you take the batch of images, XB, and you fit it into the model, right? So the model gets that and it'll predict your classes, YPred. Then you have your loss function. So this is exactly what we've done before. And it'll take the loss function will take YPred and compare it to YB, where YB is what? The real labels, right? So you're essentially doing the same thing as before, minimizing that error between the predicted labels and the real labels. So you calculate the loss, and then you do the familiar 3 steps, right? Which are opt 0 grad to zero out the values, loss dot backward to perform the calculus part, the calculation of the gradients, and figure out if you should add or subtract from the weights. And then finally, once you've calculated all of that, you go ahead and you update the weights. So this is always in there, right? And then after that, this little function here just prints out the loss value because we want to see it going down, right? So that's essentially our goal. So let's go ahead and run this train loop. Now, I'm going to go back to this, and I'm just going to instantiate all the elements. And again, this is very similar to what we've done in the past. All right, so this time around, our model is going to be a classifier CNN. There you go. The optimizer, just like before, is torch.optim_atom. Remember that the parameters from the model are mapped to the opt, and we provide the learning rate here. As I said, the loss function is cross entropy. We did a whole lecture, right, on entropy and cross entropy and all that, if you remember flipping the coin part. And then finally, we just run the train loop, which takes in the number of epochs, the model, the loss FN, the opt, and that returns a list of the losses. Any questions? Once I run this, it'll start training. So let's take a look. It may take some time. Oh, really? Yeah. So, yeah, exactly. So how long do you think that, like 30 minutes? Yeah. Yeah. So as you can see, I have an especially slow computer here. So with a CPU, this is going to be slow. Now, consider the competition. They're not just black and white images anymore. They are color images. So now you have 3 times as many, right? So you have R, G, and B. So it's going to be even more memory. So this requires the use of GPUs, especially because you want to try different things, right? And you can't you can't just wait like 3 hours to see one run and then do another run. You want to be quick and modify quickly. So having a GPU is really nice. But essentially what we're looking for is we want this loss to go down, right? And then once the model is trained, we're going to evaluate it. So if you look, my model is pretty good, right? So it's the F measure is 0.989. So the MNIST data set can be solved really well with a CNN. You guys see that? All right. So now, so this is actually a good point where we can see it's still running, where we can try this with Colab, especially for those of you that have already run it, right? Hopefully we can get it to work. So the key thing is loading that data, but let's try Colab. So I have my Colab open here, and we can kind of like, if we're successful, benchmark all of this. So I'm going to add some libraries. Run it. And I'm sure some libraries are missing. Right? Apparently, it's got first vision. So errors. Okay. So let's do the next one. So now scalar metrics. Oh, and I didn't, so I made a mistake here. Let me select the runtime. I'm going to change the runtime to T4 GPU. So T4 GPU, I'll rerun it. So T4 GPU. And obviously, I guess you guys can, if you pay, you can get a A100 or something. It's much more powerful. Okay, so save. All right, so I'm going to run this again. All right, so that ran. So now let's go and copy the sklearn part. So that's the sklearn part. Then this one. I really like Scholar, to be honest, but one thing I will tell you guys is you should learn Colab, especially if you ever go into a data science job, because when you do the job interviews, they're going to give you some kind of a code practice thing, and it's very likely going to be in Colab. So knowing it is useful for that. If you want to get the job, you want to show that you can. It's not, it's the preferred solution, I think, of most people. It's kind of free. All right, let's look at this. So these are the variables. So I won't even, I'm just gonna run these. So this is the part downloading the data set. So here we're just using it from the datasets module. Okay, so that downloaded nicely. And if you guys have done this already, please raise your hand. Let me know if you see any problems or report any issues you had. Well, now we're gonna do the train set. Okay, so that ran. And then the transforms part. Right? So that's train, forge tensor. This is the pass. And run. All right, so that's running. All right, Okay. Then we can put into shape. There we go. So 6,000, 60,000, 29. So you have to understand that we're using it. So this is the easiest code that you'll ever have for CNNs because we're using a library and the library has already formatted the data set exactly how Torch expects it because this is an example. But Scifar will require a few additional lines of code for us to reshape the tensor in a specific shape. So you'll see that when we get to Scifar. All right, so then here we created the data loader. This is my data loader. Hit run. Okay, that's the training one. Then we use test. Test data loader is done. I'm going to add a few more lines of code here. Okay, now the metrics function, right? So we have our metrics function. Next should be the architecture. That should be this one over here. There we are. Okay, let's copy that one. Oh, whoops. Yeah, there it is. Oh, well, that's the same one. All right, the check is there. So that's good. Then it should be the training function. Train loop. Control copy. Yeah, there it is. And now we're just gonna grab, we're gonna insert. So far the CPU has only done one iteration. All right, then I'm gonna do control copy. And once I do this, of course, it's gonna start training, right? Because it's gonna invoke the training loop. So let's go ahead and try that. All right, so it's currently here. So this one is still on the first. Okay, there's the first iteration, right, with the GPU. Any questions so far? So it's this has actually turned out to be a good example because it shows the code is exactly the same, right? Literally. Whether that's one of the nice things about Torch, like one of the very exciting things. I think I've told you the story in 2014, 15. I was trying to implement neural networks and things like that. There was no TensorFlow or Torch at the time, so I was trying to use Kubernetes itself. And it's in C++, and you have to think in parallel. But then, very smart people got together, created these frameworks, Torch, TensorFlow, with the goal, okay, the code has to be the same regardless of whether you're using a CPU or a GPU. So they created this concept of a computational graph. Essentially, you create the whole thing, the network, and then you just say, no, I want to run it in CPU or I want to run it in GPU, and it's the exact same thing. So later we'll see that we do sometimes have to make a few tweaks here and there. to specify in the code some things like I want to put this on the GPU, right? So, but we'll cover it. We'll get to that. But for this example, it just works perfectly. So if you look here, my code is still running on the CPU. It's on the second iteration, whereas on the GPU here, it's still running on the third iteration. So, yeah. So, it makes sense in a competition. You want this because you want to run one thing and then try another thing and then another architecture, right? And so this makes it so that you can do that. Otherwise, you'll run out of time before you can several iterations. All right, so this one is still at 2, whereas the GPU is already here. So this will do, I think, let's see, original code. So it's about 20 iterations. But it's going to do training. So I guess while that's happening, you can start copying some of the code. So once a model is trained, what you're going to do is you're going to run this piece of code. I'll just start describing it right now. So remember, you a lot of the time you're going to use this with torch.nograd. So what that means is when you run the test set on your model, you're not going to update the weights. Okay, that's essentially it. So whenever you use that statement with torch.nograd, you're essentially evaluating your model on a separate test set, but you do not want to update the weights given that data. So once that happens, notice from testDL, right, you grab X real and Y real, you plug it, which is a batch of images, or the 1,000, actually it's the 10,000 images all at once. You feed all those 10,000 images into the model will predict the labels. Because of the way that it does it, we're going to have to use Torchmax to select the actual indices, and then essentially we can invoke our print metrics function and give it the predicted labels and the real labels, and it's going to give us our confusion matrix and also our precision recall F measure. Does that make sense, guys? Any questions so far about anything? So the format of this is actually very similar to the SciFar 10 challenge. As I said, with SciFar, you just have to, there will be some things that you need to modify. And it's color images. It's different. But now you can see that you have at least here a framework that can help you to train your model a little bit faster. Yeah.
Like active tensor, um, is how are you getting nerds to do multiple?
What do you mean multiple? Are you saying that you have here, I have several and you only have one? So I think what may have happened is the mistake that I made in the beginning. You have to select the GPU. You have to go to runtime, change runtime type. Do you see this?
Yeah.
On that. And you have to select T4 GPU. Oh, you have T4 GPU? I don't know. But yeah, it should be running on, I mean, you'll have a GPU just like the one I have. This is running in the cloud. Yeah, if you're using the code from this, yeah, from the, I didn't change anything. How about the rest of you? Are you guys running this? Today's a good day to practice with Colab and feel for it. Yes, sir. Which line? Mhm. Oh, with printing the image, you mean? I didn't print those. Yeah, we don't need that one. But I see what you're saying. Your problem is this one here, right? What's the error? What does it say? All right, I'll take a look. Hold on. So the rest of you, I'm recommend try to get MNIST to run in colon. Yep. Yeah. So here's the answer. So MNIST STR is not defined. So that's MNIST. Yeah, so you're missing. So you see there's a variable called MNIST has underscore TR. Yeah. And I don't think you have, I think you skip ORs. So, so I'll show you. So yeah, right. So the data first is going to be from data sets, then it gets transformed into this. So I think you're missing this cell here.
Yeah.
Yep. Just double check. Any other questions, guys? Again, this is your chance today to get to play with Colab and kind of because this is crucial for it's actually the reality of the world, right? So the reality is if you're not Google, if you're not Facebook, if you're not, what's the other big one? OpenAI, you just can't compete. Let's say that I know everything about GPTs and transformers. I know everything, let's say, right? And I have all the data. How am I going to compete? I only have one GPU at home, right? They have 650,000 and they can put them in a cluster. And they have an army of yeah, so it's impossible, right? And that's the reality even for this competition. I'm pretty sure that the person that's going to win is the person that uses a GPU because they'll be able to run more times, try more things, and so on. Try deeper architecture. And that's why I've done stage two. Stage two, you're using a ResNet, which has not just 2 convolutional layers, but at least 16 or 50. You can have as many as, I think, over 100. Right? So a lot of it is, so essentially, I think I've said this before, but there's a law that says right now, they've like discovered this law for language models. More data, more computing power, more depth of the network, better model, guaranteed. They call those the scaling laws. But anyway. All right, great. So this is hopefully still training. There it is at 15. The losses are going down. When you see these scientific notation, you can see that they're going down. The what?
It'll go down, it might go up,
Yeah,
and it'll go down again.
the CNN is pretty good. So what that tells me is that this is overkill, probably. We could have done fewer epochs. The model was pretty good already at the beginning. Because remember, at the beginning, this serial loss, it's already seen all the data. Remember, right? So the first, and we're not even printing, I think we're printing at 0, and then we have to look at the logic. But just in the first few iterations, when it looks at the whole data set, it pretty much found the pattern and it figured out how to solve. All right. So we're at 16 iterations. Let's see my CPU, right? So let's go back to my CPU. It's only at the 3rd iteration. So you still have 17 more to go. So you can see here in this example, the reason why you really want to have a GPU. So remember, for stage 1, you can use CNNs, but this essentially, this approach. Just no transfer learning, no resonance, nothing like that. You have to essentially train your model from scratch. You can't borrow someone else's weights. All right, so we're almost done. Yeah, you're right. So look at this. It's kind of a high value compared to everything.
Yeah,
But it should be fine.
the early experiment. I'm sure.
It won't. No, it doesn't. Because it's going to do more. This is kind of like a one. And what you can do, actually, if you're concerned about that, is every time that you print one of those, you can save the model. That's called a checkpoint. And you just save it as checkpoint 1, checkpoint 2. And then you look at all of these and you could select the lowest one and then just use that checkpoint. And that's the model that you can use. Do you see what I'm saying? That kind of goes to Onyx, right? In Onyx, I'm telling you, you can train the model, but then you save it as a file to use on a website for inference. No, you're not going to train it anymore. You just use it. So this is the same. You can always save these models as checkpoints. In fact, when you guys use ChatGPT every day, what you're using is a checkpoint of ChatGPT. All right. All right. So we're almost done, I think. Oh, it's done, right? So it finished. It, see the check mark there. It did 19. So now we run this one to measure performance. And there it is. There's your beautiful, that's a beautiful confusion matrix, right? You want all the values on the diagonal like that. Remember that this has 10,000 that's 10,000 samples and 10 classes, right? For MNIST, it's the handwritten digits, a 0, a 1, a 3, and so on. But as you guys understand already from confusion matrices, what you want is for these values on the diagonal to be very high. They're almost all over 9, almost 950, right? And then you want very few. There's going to be a few mistakes here and there, but that's fine. And that's what we have the metrics for. These metrics are essentially amazing. Accuracy is 99, precision 98.989, recall, and then the most important, which determines the winner, is 0.989. Whoever, so that's a really good score. Got it, guys? Obviously, with MNIST, you can do this because MNIST is a very academic data set, basically from the 80s, right? And then SciFar is meant to be a better reflection of the ImageNet competition. So you guys will be using MNIST. Yeah, so we finished this script, right? So we're done with that one. So that's really great. We did it in Colab, which is really pretty amazing. So that's great. Now the next challenge that I recommend that you try to tackle with Colab is how do you load the SciFar 10 data set on here? You see what I'm saying? Because there I've provided the zip file. And so I'm sure there's a way, but you'll have to, maybe you have to load it into, what do you call that? Google Drive. Because you can link this to Google Drive. So maybe that's fast enough. What's that? Yeah.
If you loaded the Google Drive, then you would be able to find it.
Mm-hmm.
Or thing that large, then I'm gonna hold the Wi-Fi.
It was very slow.
Like an hour or something.
Oh, really? Oh, wow.
Yeah. No, I'm wondering if the file uploaded the them.
Yeah, the
That's the thing.
SciFar should be on zip. When you load when the code starts to read those images, they should be from the unzip file. So you need to. So what I've done in the past, because I haven't tested this with Colab, but with Scholar last semester, students loaded all the images onto Scholar, and then they the file, then unzipped it, and then they had the folders, and they just access from their drive.
I don't know effectively.
Yeah, that's
If
something
you
that.
did it the full raw, it's gonna be a very long time.
Yeah. Well, that's what I'm saying. I don't know on it. I haven't tried it, so we have to figure that out. That's one of the challenges right now. If I can hop on, no, I think I deleted all that. Actually, I don't have it anymore. But we'll figure it out. But yeah, that's the challenge right now. Loading Scifar 10 to Colab so that we can read the data efficiently. All right, so let's actually this finished and we were able to get metrics. Let's go back to my original code. So as you can see, it's still going, right? So I'm gonna kill it at this point. I think I've made the point, right? This is not the way you want to go. So I'm gonna kill this. Now I usually what I do is if I just want to say sit on my couch and and not use a GP, just use my laptop for whatever reason. What you can do is just grab a sample of the data set that's much smaller and just use that to kind of debug the code, make sure everything runs. Once you've debugged and once you think the code is ready to go, then switch it over to the GPU. Also, especially if you're paying money, you don't want to develop on the GPU. See that? So you can just, use like a random sample of the data. But anyway, I'm gonna kill it here. All right. There's a couple of things that we still need to talk about related to this code. So I want to finish my example Jupyter notebook here. So we've done basically this part, and we completed this, and that's it. So as you can see, the next part that I want to address is figuring out the convolution maths for your model. So what I mean by that is essentially you want to figure out in the architecture what this value is, right? So how do you get that number? Because you have to hard code that number in there sometimes, and so you have to know how to do it. So there's several ways of doing this. I have my preferred way, and that's what I'm going to show you. So let's now do some examples. So one thing that I like to do when I'm playing with neural networks is I just like to create random data. I create random data with the correct shapes and then just play with the thing. And then I can figure a lot by doing that. So let's try that. So let's do an example here. I'm going to say that I have one batch. I can do this on the CPU. So let's say more examples. More examples. Okay. So here I want to just create a random data set of a set shape, and then I'm going to do some convolutions, and I just want to print out the results of that. So I'm going to do batches just one, although we can change that later. Then I'm going to create a tensor. And this, notice it's just a torch. I'm going to use the function torch.random or ran_n. And this allows me to create tensors of specific shapes with random data in them. So notice it's going to have one batch. It's got one channel. So it's grayscale. And it's 28 by 28. So essentially, this is MNIST, right? So now I'm going to print it. And you can see it's 1 by 1 by 28 by 28. Do you guys see that? So this is a very nice and efficient way of figuring out the maths and the shapes of your tensors. So now let's go ahead and create a convolution. So you can see here, I'm going to use nn.conv2d. I'm going to say that the input is one channel because MNIST has one channel. I want 16 filters, right? Just like I did with my CNN architecture. The kernel size of the filter is going to be 5, so it's 5 by 5. Stripe 2. All right, so I named that mass conv1. And notice that what I'm going to do now is, this is the model essentially, and I'm going to run this tensor, my tensor underscore test through it. You guys see that? So it's going to take that tensor and do a convolution on it, and the result is going to be stored in ResCon. And then I just print a shape. So there it is. Now, the original image was 1, 1, 28, 28. After the convolution, it is now 1, 16, 12 by 12. You see that? Pretty important. Got it? Right? So this is how you can then figure out dimension. Right? So that's just one example. So let's now do a second convolution. So now I'm going to take rest conv 1, right? The output from the previous convolution, and that's going to be the input for the next convolution. This one is going to be mass convolution 2. So this one is going to be an NN convolution 2D. Notice it's 16 because this is 16. And then I'm going to say 32 filters. The kernel size of each filter is 5, so 5 by 5. And stride equal 2. So remember, it's max pooling it, right? So now I'm going to run it and print a shape again. There it is. So it is now, notice it becomes much smaller, right? Think about the size initially. It was 28 by 28. And then now it's there's 32 versions of it though, because there's 32 filters, but they're only 4 by 4. You guys see that? All right. And then I can reshape. So this is an example of reshaping. So tensors have this property called view, this function view. And given this function, you can give it a tuple of shapes and it'll reshape it. So in this case, I'm saying that maintain the first one, the number of batches, which is 1, but reshape the rest into 1 value. So if it's like a cube, it's going to flatten the whole cube. Do you guys see that? Like it takes the whole cube and flatten it. Does that make sense? Imagine a Rubik's cube, right? And you just and make it into one single vector. So now let's print a shape. And there it is. So now it is, instead of being 1, 32, 4, 4, it is 1, 5, 12. Got it? This goes back to the beginning of the semester, right? Those tensor operations are really important. The master these. That's one of the keys, right? And so that, we're just playing with the tensors, reshaping them, stretching them, figuring out what's going on. All the data is there. Okay. So that's like a flatten operation is what I'm trying to demonstrate. All right. So now you can see it matches. Here is now the architecture from our problem, right? So if you notice, NN sequential, conv2D, but notice it's a little bit different because I have 3 here. That indicates that I have 3 channels. This is 16, kernel size 5. I have a leaky ReLU instead of a ReLU. I'm doing batch normalization, which if you notice, there's 16. This has to match. Then I'm doing a max pooling and then a dropout, which is something else that I haven't covered yet. And then the output of this will become the input to this. So notice the 16 matches here, right? And this has 32 filters, right? And that's it. So I'm creating a different architecture for color images. Over here. All right, so run that one. And now I'm going to need a data set that's going to fit in here. So I'm going to say also that I have 10 batches this time around. So that's 10 samples instead of just 1. A few more cells. Okay. So here we are. Let's try it out. So what is this one? So I'm going to create a data set, torch ran, n batches, 10. Notice the 3. So this implies that this is an example of color images. And then the dimensions, notice, these are much bigger images, 256 by 256. is about the size that ResNet expects. So I'll create my data set, and then I'm gonna run it through this model, large maths model, right? So it goes in here, and then I'm gonna print out the shapes. So originally the shapes are this, so I can probably that there, print the shapes. Oops. Dot shape. All right, so let's try it. So it's 10 by 3 by 256 by 256. A batch of 10 images, color images that are 256 by 256 each. And then I'm going to run that tensor through this. All the convolutions are applied, and it produces a tensor that is 10 by 32 by 15 by 15. Do you guys see that? So that's, you can create any architecture and then just run this so that you can figure out these dimensions. Okay. So now that we've done that, we can reshape again, which is equivalent to flattening. So I'm going to do, you obviously don't flatten the batches, right? You still want to maintain those batches separate. Each image should be a separate thing. But so I'm just going to leave this as n batches, and it's going to figure out the next dimension. So 32, 15, and 15 are, spaghettified. So you print out the shape, and that's 7,200. That's big, right? It's pretty big, right? So that tells you something about, that this requires, it'll take a while to train this model, for instance. Okay, any questions so far, guys? Yeah, so this is the process. All right. Here's another example. This one is grayscale, so it's more like MNIST, like the data set we were working with today. Right, so same thing. Notice it's got one channel, so black and white, 16 filters, kernel of 5, stride 2. And then here is 16 is the input, 32 filters. So we can instantiate that. All right. We have 10 batches. 10 batches. All right. And then now we're going to run our MNIST data through, or we create the MNIST data, actually. Let's do that. So a tensor, 10 images, batch of 10 channels, 28 by 28. That's my tensor test. And my tensor test then goes through this maths model, and we're going to print a shape. And you can see this one is 10 by 32 by 4 by 4. Okay. Now I should say that there are like equations and a procedure process that you can do this by hand. Like you can look at the dimensions of your CNN and figure out all this, but I mean, I don't see the point of that. I just usually do this instead. All right. So now we can do the same thing again. We can flatten it with view. There it is. Same as before. So 10 by 5. All right. So finally, for this problem, right? So for today's MNIST data, let's find 800. So find the 800 value. All right. So how do we do that? So we need to recreate this. So batches of 10, we already have that. This is the exact architecture that we use today. Right? So we have two convolutions, black and white images, 16, 1632, and now there is the flat here, right? So there's that value. Okay, so that's going to give us the number 800. So click on that. So now, let's see. I can use the same data set, train DL, instead of, or I could create a tensor. Either way is fine, but let's run it. I think that's still in memory. There it is. So this is the actual data we're using, right? So it's coming from our train DL. I just grabbed the first batch of X data, and its batches are 32, as you can see, channels 128 by 20. So this is our exact data that we use. And now you can just run it through the architecture and then figure out that value. So the next step is this one. So all I have to do is create a random tensor, but that matches these dimensions here. Okay? So 1 by 28 by 28, and then this tensor I run through my model function, this one, and then essentially once I get this, I print the shape and I will know what the value is because I'm doing the flattening operation inside the architecture instead of using that new function that I was using. And there it is. See that? 800. Does that make sense? So that's when you guys do your, let's say you decide for 10, it's not going to be 800. It's going to be some other value first. So you'll have to figure it out, but you can do it this way. So this 800 should be that right after the file. Any questions on this idea? Makes sense? Everyone good? Great. All right. So it seems like you guys understand CNNs. So that's good. So that was the last of it. Um, but I think you guys understand CNNs. Just sign off here now. So, all right. So that's great. So we're gonna move on to other topics then, starting next week. Um, so for the rest of today, so let me actually stop. So that concludes the lecture for today. I'm gonna stop this.